Thank you for your introduction, and I'd also like to thank organizers for giving me this opportunity to look here. I'm Hinako Asaoka from Ochanomizu University, and today I'd like to talk about quantum autoencoders for image classification. Today's main topic is going to be algorithm for quantum gate computers. But it is derived from previous work in quantum annealing field. So I will also introduce quantum annealing method as an introduction of my talk. So this is outline for today's talk. At first, I will talk about some previous studies and then introduce our proposed method and its results. So as an introduction of this work, I want to introduce our previous work in a quantum annealing field. So we propose image classification model that utilized a method called non-negative binary matrix factorization, NBMF in short. NBMF was initially proposed as a generative model trained using a quantum annealing machine. And it is a matrix factorization method. So it decomposes this original matrix here to two matrices here. And when this original matrix consists of image data, this real matrix here, this consists of features obtained from this original image data. And this matrix on the right side, this represents which phases to choose from this real matrix W here to reproduce this original matrix with. And since this H matrix is a binary, consists of binary vectors, it can be quantum annealing machine can optimize the combination of features to choose from this W matrix. And quantum annealing accelerates this training method. So originally, NBMF was method to reproduce this original input and to extract features to reproduce the original. But we expanded it to the classification model by attaching the regular information here below this original matrix. And by this expansion, regular information goes into this W2 part and could be utilized for classification of images. And we found mainly two advantages in image classification by NBMF. First, it has shown high performance in classification and compared to other classical machine learning algorithms at a small amount of data features and training epochs. The figures below shows the test accuracy at each variables. And we can see that the blue light here, this is a result of this NBMF, and it is higher than this red lines, and in this when values are small number. These red lines are a result of classical machine learning method fully connected neural network. So this result shows the advantage of utilizing a classification model inspired by the generative model. And also by using quantum annealing solvers for training with that NBMF model, computation time became faster than classical solvers. This table here shows the computation time for optimizing binary matrix by NBMF method. And annealing time for this quantum annealing solver is much faster local simulated annealing solver. So this result shows the advantage of machine learning by quantum computers. So since we have shown some advantages in the image classification by a generative model and quantum circuits, we believe that there are some advantages in a same approach by quantum gate computers. So in this work, we propose the utilization of a generative model trained by a quantum circuit to the image classification task. So the conversion of classical generative model to this quantum circuit learning is already proposed as a previous study. And since what we propose is how to use this method to solve the image classification task. And since this model can be trained by quantum gate computers, computing is to be much faster than classical solvers, and same as a result of NVMe. And also we expect that high performance in classification as an effect of utilizing generative model. So the aim of this work is to present those advantages. Then before I introduce proposed method, I'd like to talk about some previous studies. The first one is autoencoder. This is a classical machine learning algorithm. And the aim of this method is to encode input to a latent expression. So input to this latent expression here. And then decode it as an output, and that it has the same size as this original input. So for example, when the input is an image data like this, it may be compressed to feature vector through this encoder. And the aim of this method is to make this output, which is a decoded Z vector, to the same image as the this original image was input. And so parameters in this encoder and same parameters in decoder are optimized to decrease the error between this input and output. And then the method that conducted that autoencoder in quantum circuit, and that is called quantum autoencoder. Its idea is same as the previous autoencoder, and it makes this output for output state from this quantum circuit the same as this input and of input to this quantum circuit. And this input psi int and state is consists of system of A and B, and this output psi out consists of A and B prime. So the aim of this QA method is to make the same psi in and psi out. So this parameter theta here, parameter theta in this U circuit, are going to be optimized to achieve the fidelity of this input and are nearly equals to 1. But since this A is same quantum state, the aim of this method can be interpreted as making this B and B prime into the same state as B, into the same state. But how we make B and B prime in same states? The answer for this question is to utilize a method called swap test. So when the states of this B and B prime are identical, the result of this swap test, which is the measurement result of this auxiliary qubit, and it becomes a quantum state of 0. So it's a probability of measuring 0 state here. In the state here is the probability of measuring 0 is maximized. B and this B prime can be estimated as in same state. So since with theta, here it is your circuit, is variable parameters, the values are going to be adjusted in the training process of QAE to maximize the probability of measuring zero here and here in the sort test. So now I explain studies. So let's move on to proposed method. So in our proposed method, we will start previous QA method for image classification. And what we did was that we encoded the label information of data in B prime state before training. So as I mentioned before, QA model's aim was to make this B and B prime state, B prime to the same state by conducting the swap test here. So when we set label information here, primarily in this B prime state, it also goes into this B state by conducting swap test here. So as a test, we can obtain label information by measuring qubits here in B state. For example, when the input image is image of level 1, like this, we encode the information that this level of image is 1 to here in the B prime state. And after training and conducting the swap test, parameters are optimized to parameters here are optimized to classify the image of level 1. But how we encode level information to system B? We use RX gate that brings the initial quantum state to opposite state. For example, when we want to encode this level 0 data as the quantum state of 0, we don't need any change in those RX gates because initial states are already equals 0. But when we want to encode this level 1 as a state, output state of 0, 1, we have to flip the state of this second qubit. So we set the parameter value of RX gate, and then we can obtain the state is 0, 1. So in some ways, we can encode maximum of 4 classes by 2 qubits. And now we will explain the result and of experiments of this proposed method. So as an image dataset for this experiment, I use an image dataset. It is 100 images for training and 500 images for testing the trained model. And there are 4 classes in dataset. And due to the encoding condition I will mention below, we resize the input image to entire set, which means equals to 64 pixels. And as an encoding method, I use amplitude encoding. The input of this encoding method takes the log 2. So the 64 pixels of data are encoded into data 6 qubits. And when optimizing the parameters theta in the quantum circuit, I use a method called Cobra that is the classical optimization algorithm. And optimization by Cobra was repeated for 5,000 epochs. So, and in this experiment, we propose our own structure of parameterized quantum circuit U. We split U into first 2 parts, form F and data is Y. And we set 2 patterns of quantum circuit in each is X and Y, and observe the difference between the results of each pattern. So in this slide, I have shown the structure of each quantum circuit pattern. In form part X, we set two patterns of real aperture circuit. And this is a measure structure in quantum circuit learning, and X1 and X2 are different in order of entanglement by CNOT gate. So the entanglement of X1 starts from the bottom qubits and bottom qubit, and on contrary, the entanglement of X2 starts from the top qubit. And then in this part M here, this is the number of how many times to repeat this squared area in the circuit. And this will be set M as 15. And in this latter part, Y, with a quantum circuit with a new proposal structure, we think that this structure is efficient for classification because it involves the entanglement between qubits in system B. As I said before, so B is the state where the level information of data is going to be encoded. So I suppose it will be efficient for high performance in classification by empowering the entanglement in that state. And the difference between Y and Y2 is only this first rotation. And this white gates, it can be set to any gates like RX gate or RY gate. But in this experiment, we set all of them to CNOT gate, which is without parameters. So let me show the results of this experiment. First, this table shows the accuracy of each circuit pattern. So the best result was when we used X2 for the structure of the formal part in parameterized circuit, and Y2 for the other part. So the highest classification accuracy of the test data marked 81.2%. Later, I will show you what was the structure of this X2 and Y2, and compare the difference between other words. So on this figure, I will check how the training in QA went correctly. And as I mentioned before, the aim of training in QA was to make that B and B prime state into the same state. So this figure shows the error between B and B prime at each epoch to check the training progress. And I compare the best and the worst results of that accuracy. And we can see that the error of the best result, which is right here, is lower than that of the worst result, the orange line. From this result, we were able to confirm that low error at training corresponds to high accuracy at testing. And next, I show the structure of the parameterized quantum circuit I used for this experiment. The structure of the best and worst results are shown here, and we can see that the difference between them is that whether they use this Y2 in the latter part of circuit or not. So from this result, we can see the importance of entanglement toward the system B. So since system B contains the level information, so empowering the entanglement between qubits in B may be efficient for a high performance in classification. So now let me conclude this talk. And these are the topics that we have shown in this work. At first, we propose a new method of multi-class classification based on QAE. And there were some qubits that were discarded in original QAE method, but we utilized them for classification by coding the level of information there. And this proposed method achieved 81.2 accuracy in classification of 4 levels. And the parameterized circuit entering towards qubits for classification were effective for high. And of course, there are still some tasks we have to work on in future. And we have to consider more efficient structure for the parameterized quantum circuit U. And Another problem is the scale of task, which was small for this experiment, so we have to check this method can solve larger problems or not. And also we have to do a comparison to other machine learning methods like NVMA or classical. So that's all for my talk, and thank you for hearing me.
Thank you very much. We do have time for questions. I actually have one. For this type of quantum machine learning models, if you will, it's very well established that the encoding circuit actually has a very big role. I'm not sure if I missed it, but did you explain what encoding method you used?
It's encoding the label information.
Yeah, for the data, taking the classical data to the
data. What I used was this aperture.
Okay.
Is just convert the pixel information to aperture or sign, of course. Set of the key.
Okay, so have you considered trying like the some like data reuploading schemes or something? So where you essentially, for example, the data to the pulse lengths of some locations or something like that.
I use this just this scheme.
Okay, thank you. There's one question over here.
So as far as I understand, your model can also do generative tasks, right? So I wonder, so you have like, I imagine, right? So you have like 100 training data sets, or there is a good balance between 4 classes. So if you generate like 100 pictures, so how about this fair sampling? So it's like consistent, right? So you have like a balance between classes. Did you check that?
I think we have checked the generation, so I will work.
You said that the entanglement plays a role here. In which sense? It's playing a role.
Sorry.
Yeah, in some of the last slides, you said that the entanglement is playing a role in the classification, but I don't see in which sense.
You mean that how this entanglement works?
So if entanglement is playing a role, if you cannot find the classical model that is doing the same with the same resources, no? So in which sense here it's playing a role.
Maybe how I did understand your question, but I think we have conducted the comparison between classical and quantum, so that is feasible for.
Right, and let's thank Hinako once more.